journey from a root files, I mean not files, root directory, okay? We start the journey to root directory, and we are aware of the directory is actually an array of this guy, okay? An array of 32 bytes items. Remember this. There's nothing special about directory, just an array, okay? And inside each array, already people talk about how to retrieve the data because you know about the NDNS problem, okay? Now don't worry, the NDNS problem, we can solve it by using a structure. Treat this as a structure of 32 bytes and extract it, okay? So I hope that within this week, tomorrow, our tutor will give me the notes and I can post it up. Then you will know what is the meaning of using a structure in order to retrieve these fields, okay? And we know that one more information before we leave last lecture. The file size itself sucks, okay? It stores a file size using 4 bytes. And remember, a file is addressed by bytes, okay? Every number represents 1 byte. So we only have a 4G minus 1 byte, okay? So we step into a next topic. This topic is something extra. So what is the extra things is before we have FAT32. Okay, I already talked about the format. It's called 8.3 file format. 8 characters for the name, 3 characters for the extension. People already hate this because at least it cannot using like a Union code, Big 5 code, GB code to put it there. Okay, and also you cannot have an extension for more than 3 characters. So people hate this and try to patch it up. Okay, so Uncle Bill or Uncle Gates, okay, whatever you want to name him. Yeah, invent another way. That way, I cannot use subs to describe it. It is awful. Okay, how awful it is? Yeah, extremely awful. I hate this. How come people will think of this? I mean, either he is a genius or he is a monster. So what is that? This is okay. The directory file, right? Directory file is an array of 32 bytes. So what are these logs? Yeah, let's go down from the first item all the way down. Okay. Now this is a way to read this array. So the first log, okay, okay, is not a normal directory structure, not a normal directory entry. It's called LFN, long file name entry. Now, don't need to care what it is. So we will skip this, and eventually reach a normal entry. Okay? And that normal entry is the one that I've shown you before. Now, what is this? What are those 3 guys? The 3 guys are only storing the names, the longer version of a big file name. Okay, only storing the name, and the way to read it back is, I know that let's say that this file is called maybe a final exam.docx. Okay, I never use docx in final exam. Okay, so don't worry that you will find this file. Now, final exam add together already more than 8 characters, and docx 4 characters extension. So we will need non-file name support. And the support is very funny. It's first declared that there is a file here, and its name will be, I don't know whether it will be like this, okay? It will be called final exam.docx, right? It will become final e1.docx. Whether the X will appear or not, I can't remember. It's 1, 2, 3, 4, 5, 6. Yeah, just like this. No one seen this before? Yes. So how many of you see this kind of thing? Well, you guys are old enough. Okay. This kind of names, right? Interesting. So where can you find those names? Now, in the specification of our assignment, you already find this. It's actually stored inside the normal entry. It is a normal entry. For Windows, the Window Explorer, if it know that it is a FAT32 and know that this is a normal entry, usually it will show you the normal entry. Okay? It will search backward to see where we have non-file name entry up there. If yes, that means it belongs to this guy. Wow, interesting. And it is a going fact. So this should be a 0, 1, 2, 3, so 4 slot. Now I find a normal entry in the slot 3. I will go back 1 to find the first part of the name. Not enough, go to find the next part here. And the third part, maybe the third part say that, okay, the name stops there. Okay? So this is how. Wow, colorful. And what is non-file name structure? The non-file structure is very interesting. First of all, it won't pretend to be a 32-byte structure. Pretend, okay? It won't pretend to be like this. So this is our normal structure. This is normal. This is the non-file name structure. What can you find? Now, look at the reserve field. Reserve. The same location we will reserve. It don't touch it. How about file attributes? The attributes has to tell you that whether this is a directory, whether this is a normal file, or whether it is with this name 0F. It means it is a non-file name structure. So some of the fields won't be touched. For other fields, they store file name parts by parts. Very interesting. You cannot use a string copy it out. You cannot do so. Because it's a high 5, not 5, hiding 5, okay, not high 5. Hiding 5 character, okay, with Unicode representation, put it here, 5. What if your file name has a 6 character, 6, let's say that this is a 6, is very hard to find, okay, or maybe it's a 0, 1, 2, 3, 5, okay. So then 6 characters, so the 6 character will be jumped here. Wow, interesting, huh? So you cannot do string copy, right? String copy. No, this is not the end. Okay, the end is here. Okay, and even more interesting is because it supports Unicode. Unicode usually will have used 2 bytes to represent 1 character. Okay, so that means every 2 bytes here, or those you can count. From byte 1 to byte 10, altogether 10 bytes. Why there are 5 characters? Because it's just 2 characters, 2 bytes to represent 1 character. Okay? So if break it into 3 parts, so 5, 6, 2, so add together we will have a 13 character per entry. Okay? And the maximum file name, including the extension of a Unicode way to store it, is 255 character. So it can be very long. Now I give you an example. Don't be shocked. Okay? What is this? I already give you some colors. I create a file name called I love the operating system called .txt. Yeah, long it out, right? So if it become the normal entry, you will find something like this. It takes the first 6 character. 1, 2, 3, 4, 5, 6. So it becomes I underscore love. Okay, it's here. I underscore love is here. And the 7 and 8 become a 2 to 1. And then extension txt. Okay, so this is normal, but since we know that before the normal we find non-file name structure, so these are the file name parts of this guy. So they only represent file names. They don't represent any file size, don't represent any cluster allocation related thing. Now, what are the colors here? I already colored 3 regions: the green, the orange, and kind of red. Okay, let me check. Where is it? Oh, my screen is red. Okay, so free range. Free range means these 3 ranges. 1, 2, 3. Okay, so this free range, I I just open it up, okay, using a hexadecimal reader to read the content, and you will find something like this. How to read it? Remember of the NDNS problem, the first character is 006D. Don't read it 00D6, okay? It's 006D. So 6D, what is 6D? I don't know. Yeah, you know? Yeah, I know that I reverse it, okay? Main ASCII. So 6D. Oh, 6D, where are you? Oh, here. Okay, you don't know that there is a main page containing an ASCII code? Main ASCII. Okay? You don't need to open up a browser and Google ASCII table. No. Main ASCII. Okay? So this is M. So 6D is M. Okay, I find M here. But I do it wrong, right? This is the last entry actually. The first entry is here, so go back here, 49. So if you have a terminal, main ASCII, okay? 49. Read it in that way, 0049 will be I. And then 005F, okay, will be underscore. So where is this dot? Because this tools will dump the value byte by byte, okay? So if you don't know what is the meaning of 00, so put a dot here. So believe me, it will be reading in this way. Is I love the operating system called .txt, okay? And when it ends, it will have the last byte or last two bytes, all filled with zeros. 0, 0, 0, 0. Last two bytes. Okay? So happen like this. Okay? And that's why you cannot, when you're doing an assignment, you cannot do string copy, string compare. Whatever string related operations will be forbidden. The first problem is because they are broken into parts. The second problem is 0. Do you know why? Okay. Where I hear a sound? Yes?
Terminate.
Right. Okay. So let me ask you something. Okay. May not everybody know about this. Okay. May not everybody know about this. So you declare a string, right? The string is like this, string, and then 10 characters. Okay. Then I write something like this. You know the meaning, right? You know the meaning. What is the string length? 0. Okay. What is the meaning here? 0. What is the meaning here? The same. They are the same. This character, /0, is actually equal to 0. They're just the same. Okay? So maybe you see some people are doing string operation, they set all the characters to 0. And because of this, okay, it means a terminator. Now, if 0 means terminator, and you try to treat this bunch of things as a string, sorry. This is already null. You cannot copy anything. Okay? So in your assignment, so what should you do? Very easy. Forget about string. Yeah, don't use string. String will cheat you guys, okay? So put it out byte by byte. Yeah. So yeah, don't think that it's stupid. It is the only way. Okay? It's the only way. Put it out byte by byte, and then yes?
I want to ask for the sequence number. Why the sequence number of LF and number 3 is?
Yes, I would say why there is a 4 there. Okay? So any questions about this 0 problem? Okay? The 0 problem, if it is a normal C string, okay, that means a termination number. Also, I missed one thing our customer already asked. What is this 01, 02, and 43? Okay? 01 and 02, okay, is actually we call a sequence number. Okay? So it means that it belongs to the first trunk of the big file name. This is the second trunk. And this is, what is it? is a last trunk, and why we know that this is last trunk? If it is going to be last one, okay, yeah, very interesting. It will OR this number to this number. So originally it should be 0, 3. Originally it's 0, 3, 0, 1, 0, 2, 0, 3. But it wants to declare that this is the end. We want to declare this is the end. So I know this is the end because of there is a 4 there. So this is it. Very easy. Okay? Yes?
What is the longest file name
I hope that it won't collide. Okay. 13 characters per trunk, and we have 255, 10 something. Still okay. Still okay. You have four you already. Oh, you still have one more bit. Right? You still have one more bit. Don't worry. Yeah. Okay. Yeah. Just encrypted. Okay. Oh, those dots are something that the tools that cannot represent. These tools usually represent ASCII code only. So if you know this ASCII code, print the ASCII code to you. But usually the ASCII code is not really mean the file name part. Let's see here. Why there's an and here? So happen that and I can print it out, but it doesn't belong to the file name. Let's treat this guy. So this green one, this is the one first name, first character. This is the second, third, fourth, the fifth. Yeah, like this. Very brain damaging. Okay, brain damaging. Yeah. How brain damaging it is? Usually we read a pair of bytes like this, right? Now I'm forced to adjust my mind. Read a pair of bytes like this. Wow, interesting, huh? Really brain damaging. Any problem? And after I extract all things, you will find this trunk. Okay, broken into parts like this. Yeah, in your assignment, yes. Back what? Okay, so the way is like this. First of all, when I scan the directory, when I find LFN entry, I will skip until I find normal entry. And when I find normal entry, I will roll back a bit to see the previous one, whether this is a long file name. If yes, it belongs to this guy. Yeah, we name very interesting. I try once. If you expand it, okay, expand the name, it will, if there is a 4 entry here, delete this 4 entries. And we create a new, let's say 5 entry couple after this guy. Just like delete. They try to delete it. And append the new five guys combos. Okay. Then go down, continue to scan until you find 5 holes. And no problem. You are the operating system. No problem. Yeah? No. His question is, what if I expand the file? It so happened that already very close to the last slot. Right? If I expand, let's say that I don't call it that I love, I don't love. Yeah, I don't love. Yeah, I don't love this. I expand the name, so I occupy one more trunk of 32 byte, but I don't have space to expand. Yes, I need the 8FM4, but I don't have space to expand. So delete this 4, okay, and find down to this, okay, where I find a hole belongs to this directory, and relocate it. No, always can find it. If no holes, allocate a new block. You are the operating system, okay? You are the OS. You control all the space. So unless there's no space, okay? Yeah, it is true. If this is just not this, the root directory, you fill it out up to the first whole cluster, you may need to allocate the next one. Okay? Interesting, huh? Or I should say interesting. Okay? I would say Uncle Bill shoot himself in the face. Okay? Or the Cantonese 執個石揼自己. Yeah. Okay, no problem, huh? So the summary is not anything intellectual, so I skip it. Okay. So now something really important to you now. What is the meaning of transferring the file content? Okay, because in assignment 2, you need to transfer the file. Okay, you need to find I need to recover this file, so I need to transfer this to find where that file is. Okay, so let's see what will happen for read and write. For the read and write, a read part is easy. Okay, the read part will start the transversing of the data block by first reading the directory entry. The directory entry contains the starting cluster address. Okay, and you find that this is 32. So what should you do? You go to the 32 cluster to pull out the cluster content, okay, and start reading, right? But what if that file is longer than, you can query the file size in this item. The item say that, okay, my size is more than one cluster, so you need to go to the FAT. Now, what is the FAT? The FAT is very simple. It is an array. That's all. It is just an array. Okay? It is an array of numbers. Each array width, our array item is 4 bytes. And every 4 bytes storing different kind of values. It may be 0. If let's say that I transfer starting from address 0, the first guy, all the way down, okay, I find some zeros. That means that corresponding cluster address 34, let's say in this example, is not allocated. Okay? This is free block, you can use it. Okay? Or you find other things like this, EOF. So what is EOF? That means the block, 33rd block, will be the end of a particular file. Okay? The file end as that data block. Okay? So you will find, I don't know why the Microsoft is always doing funny things. They have one more representation, okay? Here, how many? Fx only, you have F9, F8, Fb, Fc, Fd, and Ff. You represent EOF. Why you need so many types of EOF? Yeah, I don't know why, okay? Ask Uncle Bill. He needs so many versions of EOF. Okay? So, next, what is it? We will have damage, okay? FAT32 allows you to mark a particular cluster to be damaged. Okay, like this bad sector. Then you mark it. Okay, so why you mark it? Because you don't want to allocate it. Now remember, a bad cluster means that address is corrupted or you cannot access it physically, not because of this FAT files, okay, is corrupted. No, okay. This FAT files is still okay. Now this is the FAT array. So when you transfer, it's very easy. Just cast it as an unsigned integer array. And you go. This is an unsigned integer array, 4 bytes. Now what's next? I know how to access it. Then I will go to a 32 and check whether the address corresponding to 42 is EOF or non-EOF. If it's EOF, that means it's the end of the file. Very good. Now, if it's not the end of the file, of course the size already carries something. Let's say the size is 1 gigabyte. Of course, you cannot have one cluster on it. So you will go to FAT, find that, here is not EOF, it's 33. The next block, okay, is my neighbor. Okay, so I will go to my neighbor, okay, and go to my neighbor, let's say the neighbor is somewhere here. Pull the data out, okay, and depends on the file size, I don't know. Let's say I have only 11 bytes left, okay? So then I will go to 33 cluster in here pull out 11 bytes, and that's all. I finished reading the file. Okay? Any problem? And here you will find EOF also. It declares that this is the last cluster belong to the file start with 32. Now, very interesting, the FAT linked list, the FAT is a linked list. It only tells you when it ends and what is my next, not telling you where is the beginning. The beginning is always in the directory. Okay, the start in the directory, the end in the FAT. My next neighbor is also in the FAT. Any problem you want to ask? So to delete or to format an entire drive is very easy. How? Mark them all to be 0. If you like, mark them all to be damaged. Yeah, no problem. Then you can successfully corrupt this. Very interesting, huh? Okay, so this is a reading. You know, the reading part is not a big deal, right? I just follow what already laid out inside of this. Now, how about write? Okay, so this is still the read part. Oh no, this is write already. So my title changed. Okay. Now, what is the write? I set up a string example. The string example is very interesting. I have a file called explorer.txt. I want to append something. Okay, to this file. Okay, don't do it unless you want to reinstall Windows. Okay, so when I go to append this file, so what should we do? Okay, now first of all, follow the linked list of the block allocation, find the last block, and continue to write data at the end of the file. Continue to give more data. Let's say I want to fill out 100 megabytes more. Okay, then I will continue to write until I find this 32 block. The ending block still should have some space, okay? Then I continue to fill it up, fill it up, fill it up. And now this already filled up by me, no space left. So what should I do? I need to, now this is very important, allocating new blocks. Allocate new blocks. So how to do the allocation? Okay? Yeah, maybe you will do the easiest thing. Okay, my last block is 33. Okay, my last one is 33. I want my next block, of course, the closer, the nicer. Why the closer, the nicer? Because the hard disk mechanically is spinning. Okay, so it's as if if it's a neighbor, so the head don't need to be positioned. So maybe the next guy is the best one. Now, the next guy is very easy to be located, but in an FAT32, something that which is documented, but I find that no operating system follow. Yeah, it's because Microsoft invented, people don't like it. Okay, so what is that? This is a free space management structure called FSInfo. Very interesting. That FSInfo tells you two things. How many data cluster left? Okay, well, very interesting, right? Because you already know that, oh, one is free, that means that I can convert into the hard disk free space. So it's very important. And what's next? Next is the next free cluster address. Next free cluster address. So it wants to speed up your search. Okay? When you try to have a new allocation, no problem. The next available cluster address already provided inside this FSInfo structure. So you just take it, okay? And after I take it, of course, I will do some change. I will do some change to FAT, update the linked list. Okay, I know that 33, the next guy will be 34, and 34 no longer, okay, look at 34. Now 34 original is not occupied. Hey, why always me? Okay. Yeah, this is just a password, okay? When I say that, it works. Okay. Now this is 0, unallocated, it suddenly become allocated. Now remember, change it into EOF already means that I allocated. Okay, but very interesting. No ownership, okay, is marked there. Okay, we believe, okay, every people writing the FS controller, file system controller, file system controlling code are good guys. They won't do bad things. So there is no need to mark the ownership saying that, okay, this EOF is belong to me. No, wait, okay? We believe everyone is honest. Okay? Yeah, what you say is correct. we can pre-allocate. Okay, but pre-allocation needs some special techniques because it's just not aligned with the file size. Okay.
Sorry.
Yes.
So the purpose of the next free cluster is to speed up the search.
Yes.
But when you take the next free cluster,
yes, that's what I want to say.
You need to search for the next free cluster and then update
Exactly.
it, so it is not.
So that's why no one cares about this. I tried it. So I tried this. While we are setting up a previous year's assignments, okay? 1 year we want to have an assignment doing raw file system right, okay? So we do one test. Every time we do change into the disk, mark this entire structure to be all zeros to see what will happen. And the result is nothing happened. Okay? All operating systems know that, yeah, Microsoft sucks, okay? Don't need to care about this. Okay? I just mark the entire structure to be zero. No problem. Okay? Well, I don't understand. Maybe next time I try other numbers. Maybe other numbers will trigger something wrong. Okay? But most of the device, I know that it's don't care about this. So that's why every time you look for a hard disk free space, usually it cannot immediately tell you the free space. It needs some time, a little time. What is a little time? It don't believe in this. So what should you do? How can you reduce the file size? Do I really go down to all files and, oh, you are 3 bytes, okay, you how many bytes you are? Oh, you are 10 bytes, okay, and do an exhaustive search over the entire directory tree and do a summation? No. What if I reset it? What if I reset that? How can I report it? Efficiency. I want an efficient way. No, I reset it. I reset there's 2 guys in the zero. And I tried it, it works. It works, it means that I don't do any damage. Still the disk go on, and every report will be still the same, still normal. So that's why I say that when you try to get the volume free space, it takes time. It cannot immediately report to you. It takes maybe 2 or 3 seconds delay in order to tell you. And you accept that, right? You will think that, oh, accessing hard disk, of course, is slow. Okay? So this is bullshit, right? Already there is a free space, but no one believes in it. How? How to deduce the file system free space in a quick manner? Don't do an exhaustive search over the directory tree. Nonsense. Any idea?
Look at the table and see which is not allocated.
What?
Look at the FAT table to see which how many slots there are zero.
Yes, exactly. Exactly. But is it not accurate? What's the meaning of not accurate?
There are some sets that will be
not fully filled.
Yeah.
Not fully filled, but what is the meaning of free space to you? To a user? To user, the free space is not equal to whole disk space minus occupied space, right? The equation should be the space that I can use to a user. Yeah, the space that I can use is mine, okay? You tell me that, oh, my flex now is $8 million, right? I cannot settle. Okay, nothing useful, right? I want useful data. And useful data is the block that I can really allocate. Okay? So their answer is correct. Just do a scan over the FAT structure, look for 0 entry. How many 0 entry? Combine it, or not combine it, count it, okay, and multiply it by the cluster size. And that is your free space. So it takes a very short time, but still takes some time. It depends on how big your FAT is. If your FAT is small already on the memory, so within 1 second you get the answer. If it's not, it's big, so I would need to do some retrieving over the hard disk. Okay? So FAT is that thing, okay? And answer his question always also responds to the original design. The original design of this free cluster address, okay, after allocated, you have a price spread, okay? You have a fast allocation, but still you help the next user or next guy to find a free cluster address. So how to do it? Usually we will do this kind of a cyclic next label search. Next label search means that I start with myself, I go down to find my neighbors, the closest neighbor with a 0, then I will put it here. If my closest neighbor search fails, I reach the end of the hard disk, I cannot find any zeros. I will walk around, go back, and do the search. And the reason is very simple. Very simple. It's because of one very famous idea. It is the idea. It is a heuristic. It is some observation. Is that we call it spatial locality. Spatial locality. Spatial means something related to space. Okay. Space locality means that usually when we put it together, it means when you need block I, when a program needs block I, an application needs block I, its neighbor or its next allocated block will usually be needed also. Yeah, that's why I said it's heuristic. Okay, usually you will need block I, and then you will need block I plus 1, also I plus 2, I plus 3, so on and so forth. Okay, so why not we try to put things together in order to try to boost up its amortized average speed, something like that. Okay, so this is what we call spatial locality. So that's why I put an extra here, and this is just some heuristic. Okay, heuristic may not be correct. Okay, there is another locality. It's called temporal locality, but it's not about file system. Temporal locality is also usually talk about caching. Okay, so our main dish. Okay, our main dish here, recovery and deletion of a deleted file. Let's go. What is file deletion? You know how to read, you know how to write. So deletion is to kind of reverse what we have done during writes. What we have done during writes, we have write data, we have allocate blocks, we have update file size. Now how about delete? Delete, do you need to undo all the change? No, you don't need to reset the file size, right? I don't want it. How come I reset file size? Okay, so no. Did you need to clean up the data? I write data previously. If I delete it, do I need to clean up the data that I allocate inside the hard disk? Usually no. Usually no. Okay, and what should be the change? The change will be only happen here. The FAT. Look for the cluster starting from your starting cluster 32 and go on to scan the linked list. Whenever I find your allocation, remove it and make it into 0. Make it into 0 so that your linked list disappears. You don't know what is your next block anymore. Okay, not the end, right? Not the end, because you still have one more allocation area, the directory entry. How to deallocate the directory entry? Although this is an array, okay, we cannot just free it, okay? To deallocate it, mark it into a special value, 0x, that means hexadecimal, E5, and done. That's all. Yeah, that's all. Now this is delete. Delete only 2 tasks. 1, look for the linked list of allocation, and in the FAT layer, FAT block, FAT array, whatever you say that, we set all the blocks belongs to user 0, make it and allocate it, and what's next? Change the first byte of the directory entry into E5. Okay, still remember the structure. Still remember the structure here. The structure here already said something. If the first byte is E5, means unallocated. Okay, so this is already documented. And now you know this is deletion. Now my question is, okay, this is delete. My question is, the data is not removed. the file related information, you only lost something. What are the things that you lost? You lost a list of blocks. But what you still have file size. You still have starting cluster number. You still have 90% of the file name. Can you do file recovery? Usually, yes. Usually, you can do file recovery. Yes? Yes, unallocated blocks, right? Right. So next I will tell you how to do it. So, when is the case that you can have 100% guarantee that you can recover a deleted file? When? At least I want to hear two cases. Discuss with a neighbor. There should be two cases that you can successfully recover the things that you deleted. Still remember the demonstration I do last week? Here, I recover a delete file, and that file, I think that file, although the people give me a hello.py, okay, very small, okay, but I can guarantee you that no matter how big it is, I can recover it. Why? Seems like to be 100% guaranteed, right? Tell me two cases, two circumstances. One of it is easy to think of, another is not. Give me a hint. It's related to file size. Anybody wish to answer?
You haven't write anything after you delete the file.
Then, in the beginning, it is the empty file.
No, what I mean is after you delete a file from the file system, you do not write it.
Right. This is one of condition. Another.
The size of the even if you write the new file, the size of the new file is small enough that it don't cover the parts of the
Still miss some condition. Okay, at least I give you an easy shot. The easy shot is the file size is smaller than one cluster. What is the file size is smaller than one cluster? Are you have the 100% guarantee that you can recover it? Now let's take a look back in the deletion process. So if you have only one cluster, or the file size is smaller than one cluster, although it's smaller than one cluster, you need one cluster, right? So the thing that being deallocated inside the FAT will be your record. Originally is, let's say that it's EOF. It becomes 0. And you still have a starting address, starting cluster address here. If, our customer already give me a very good answer. Before you do a recovery, you have to guarantee that that block is not being recycled. Okay, it's not being recycled. Let's say it's not being recycled. Then here is the starting cluster address. I only have smaller than one cluster data because here, some dots here, one of the dots is file size. I use file size. I know that, okay, it's within one cluster. I go to this FAT32 address, crawl the data out, and we relate to the file size, okay, 4 bytes, then I pull the first 4 bytes. This is my original file size and original file content. This is file recovery. Now, how about big file? How about big file? Big file is a little bit tricky. Big file, how to guarantee that I have 100% recovery? The thing is very important. The disk should be very, very seldom used. And I shouldn't say very seldom used. It should be from the last time it get formatted to the point that you delete your file, the time is very short. and you didn't do many changes to this. Why? Because of, okay, here, because of this writing strategy. The writing strategy of an FAT32 file system loves to have continuous allocation. This is its habit. The habit is going to be allocated continuously. So when it is being deleted, you can guess, right? Let's say that I already know that what is file size, because file size is here. I know the start, I know the file size. Let's say after I do a calculation, I need 10 cluster. Why not we give a shot from this point onward, go down 10 cluster, get all the things, and make it back into my file to see whether this is my file or not. Usually the file is yes. This is my target. Okay? Usually it works. Okay? I use this trick to rescue more than 5 GB of data in a deleted, not deleted, and so happen accidentally format SD card, 5 GB, using this strategy. Yes, what if it's not continuous? Last time I showed you the photos, right? Half of it has people, has some text, another half have garbage. Okay, that's the case that I use this strategy, but so happened that the thing that behind my starting cluster address being allocated by another guy, then I cannot recover it. Okay, but still better than none, right? Yeah, better than none. Already have a very nice tricks, okay, to recover things. Okay, of course, we may want to know how to securely delete the things, right? So I think this is not a secret, right? Everybody knows that I can recover the disk. Okay, give me your hard disk, I can crawl everything. Then you have to delete it. You already know about this. So people already are looking for secure deletion. Secure deletion, now don't do this. This is not deletion. This is you only corrupt the IC port. Okay, you just damage the IC port of a hard disk. Okay, the disk itself is not damaged. Okay, so this may not work. So there are people already think of some interesting way. First thing, I love this. Right? University Wi-Fi wall. It become an exclamation mark. ED room. What? Okay. Give some time. Good. Yeah. So, I suppose some people here is from physics. You already know what is Degausser, right? Degausser is something related to a VM wave. Okay. So this is a really something equipped in data center or some. Some people want to have some protection to their deleted data, and you can buy it from eBay, Amazon. Okay. Right. Extremely expensive. Okay. No problem. So what is that? Look at that. Okay. Instruction: insert hard drive. Push the erase button, and okay. Don't think that it change in another hard disk. Okay. Still the same hard disk. Okay. Suddenly become another one. Yeah. Okay. What is that? It uses a high energy EM wave shine over the hard disk, so as the damage is a magnetic structure. Yeah, you know it's this magnetic structure, the same data, right? So use EM wave, high energy EM wave, shine over it, so that the magnetic structure is gone, and this is the ultimate deletion, right? But our customer already suggests a price tag. The price tag is more than $100,000. Yeah, I guess we can ask physics people to ask for some radioactive stuff, okay? You have some radioactive for it, okay? And I guess the thing is just the same, okay? Yeah, but you may die because of that. Okay. Interesting, huh? Okay. You don't love this. You don't love this. Okay. Too expensive. I don't know why this company already changed into another company. Okay. They sell bags. Okay. So I have to do a Google search. Data destroyer. So we still have some data destroyer thing here. Something like this. Did you ever see this? Insert a CD and crush it into pieces. Okay. How about a hard disk version? Do you see the hard disk version? There is a something. Okay, have a lever here, and when you pull it, it will pull a hole through the hard disk. Just like, okay, then suddenly have a hole in the hard disk. Okay? Interesting. Data destroyer. No, let me find out, can I find those images? CD data destroyer. Any of a hard disk. Wow. Huge machine to trash CD. Any hard disk version? Hard disk. No. No hard disk version. Yeah, basically it's just physically. Oh yeah, I found it. Before, after. Yeah, this time it's not make a hole, okay, but bang it. Will it bang? Yeah, it will. It will bang. Yeah, data destroyer. Okay, but I think that those solution does not fit your budget, right? First, you need to buy the apparatus. Also, you lost the hard disk, right? You don't want it. Yeah. Right. So she already gave me a very interesting idea. How about I write zeros? I write zeros to the hard disk. Yes, that's the way to securely delete it. Okay. Some years ago I can still find a document. The document is about a U.S. Department of Defense how to securely delete a file. They write random data. Write random database over the hard disk 16 times. So pass 1, pass 2, pass 3, 16 times. So that because some people, this is the research paper. The research paper tells us that, hey, if you really write zeros, okay, the magnetic structure, I don't know how people find it out. The magnetic structure, if you write zero all the way, write the same bytes, you can still dig back the old data magnetically. I don't know how. Okay, ask physics people here. Okay, so they call it magnetic strips. Okay, so the Department of Defense say that no, we cannot write zeros. We write random data, but still people may guess, oh, you use this random seed. Okay, then I know how to recover it. So they choose 16 times different random seed. Write it 16 times. No one can recover it anymore. Wow. Or if you believe in a Mac, okay, Mac already have a way to secure delete hard disk, okay, format it, and there is an option. The option asks you whether you want to securely delete it. Usually when I sell my MacBook to others, okay, before I sell it, I will do this. Okay, in the installer, okay, the installer asks me whether I want to securely delete. I will yes. Erase it. Okay? So let's have a break. Interesting topic, huh? Right. After the break, few more slides, I will end this topic. Okay, and we'll go to memory.